Hello friends, today we will discuss Superpave mixed design procedure as given in MS2 7th edition. And this design procedure was the direct outcome of Strategic Highway Research Program SHRP, and here Superpave stands for Superior Performing Asphalt Pavements. And this procedure was developed to replace Weem and Marshall methods. This initiative was taken to improve material selection and mix design by developing a new mix design method that accounts for traffic loading and environmental conditions, a new method of asphalt binder evaluation, and new methods of mixture analysis. The Superpave mix design method consists of 7 basic steps: selecting the asphalt and aggregate materials, developing an aggregate blend meeting Superpave requirements, mixing aggregate and bitumen, then sample preparation including compaction, density and wires calculations, and then selection of optimum binder content, and finally moisture susceptibility evaluation of the mix. So the first step is selecting asphalt and aggregate materials. A pavement mixture will not perform successfully on the roadway unless the appropriate binder and aggregate materials are incorporated into the work. Asphalt binder is selected based on environmental and traffic conditions, and this can be done using the procedures described in different IRC codes, MORTH specifications, or Asphalt Institute publication MS26. The grade of the asphalt binder to be incorporated into the design is usually specified in the contract document. The mineral aggregates. Certain aggregate characteristics are essential to design a well-performing hot mix asphalt, and these characteristics are broken into two categories. One is consensus properties and another is source properties. The consensus properties specified in the Superpave system are coarse aggregate angularity, fine aggregate angularity, flat and elongated particles, and clay content. The criteria for these properties are based on the traffic level and position within the pavement structure. The materials near the pavement surface are subjected to higher stress levels and require materials of higher quality than mixtures that are located lower in the pavement section. And when I say lower, it means more than 100 millimeter from the top surface. This table gives you the requirement of these properties, which we call the consensus properties. Coarse aggregate angularity, that is CAA, to be determined as per ASTO method, fine aggregate angularity, sand equivalent value, and flat and elongated particles. Now these properties are dependent on the design traffic in terms of million standard axles. For low traffic volume, we can relax the properties, but for high traffic volume, you should restrict to the specification as far as possible. Now here 85-80 means that 85% of the coarse aggregate will have one or more fractured faces, whereas 80% will have two or more fracture faces. Now this test coarse aggregate angularity is not applicable for aggregate size 4.75 mm and down. Fine aggregate angularity is to be determined as per ASTO method T304, and these are the maximum values of flackiness and elongated particles, 10%. The another property is what we call the source properties. Now the source properties are the requirements specific to local area because of the variety of aggregate types available in different geographical areas. And these properties are suggested as here. That Los Angeles value, the durability test, that is sodium or magnesium sulfate soundness test as per ASTO T104. Then deleterious materials, clay lumps, which are friable particles or lightweight clay particles. They should be less than these values depending upon the design traffic. So these are the tests to be conducted on aggregate before they are declared suitable for use in the hot mixes valve. The second step is aggregate blend. And in aggregate gradation, certain control points are specified in Superpave mixed design procedure. This is nominal maximum aggregate size for 37.5 mm. Percent passing at this size should be 90 to 100%. Similarly, if NMAS is 25 mm, then the percent passing at this sieve should be 90 to 100%. Another control point is at 2.36 mm sieve size. These are also specified for different NMAS of aggregate, and these should be strictly adhered to. And the third control point is at the filler level, that is 0.075 should be 0 to 6% in case nominal maximum aggregate size is 37.5 and 2 to 8% if it is 19 mm. The third step is mixture requirements. Now Superpave gyratory compactor is used to compact the specimen, and this compactor has ability to measure sample height after every gyration, and it enables the designer to estimate GMB, that is bulk density of the mix, at any specified height of the specimen or any number of gyrations. As to R35, that is specified levels of laboratory compaction, that is density at 3 different levels of gyration based on expected traffic loading. N initial, N design and N maximum. This N initial is the measure of compactability of the mix and is based on the estimated field density obtained behind the screed before compaction. Mixtures that compact too quickly may be inherently tender to compact and would therefore be undesirable. This initial gyration density specification range from 89 to 91.5% of theoretical maximum density, that is GMM, depending upon the traffic level. This end design, that is the number of gyrations is specified to reach the target density of the mix, and it is based on estimated field density in the middle of its service life. And it is generally taken as 96% of the theoretical maximum specific gravity, or you can say corresponding to 4% air wires. N maximum is an estimate of the final density expected in the field at the end of its service life after years of further densification by traffic, and it is capped at 98% of theoretical maximum density for all traffic levels. That means the air wires at the end of design life should not be less than 2%. Low air wires in field result in plastic mix that ruts easily and should be avoided. The practice is to compact specimen to end design gyrations, measure the density, and then back calculate the density corresponding to N initial gyrations. For Nmax gyrations, separate specimens are prepared at the design binder content and then they are compacted to Nmax gyrations, and the density so obtained is checked for compliance with specifications. And this table shows the Superpave compaction parameters based on expected traffic level from ASTO R35. What should be the N initial, N design and N maximum value for different design traffic levels? Once the design gyration levels were established, the initial and maximum gyration levels can be estimated using these equations. N initial is N design to power 0.45 and N max is N design to power 1.10. The equipment required is gyratory compactor, and this compactor consists of a reaction frame, rotating base hair and motor, loading system, loading ram, and pressure gauge, height measuring and recording system, mold and base plate, and specimen extruding device. The main parameters governing the compaction efforts are the vertical pressure, which we call the ram pressure. It should be around 600 kPa plus minus 18. The gyration angle of the mold, which is set at 1.16 degree. Gyration rate is 30 gyrations per minute, and the size of the mold is 150 millimeter. The thumb rule is that the mold diameter should be at least 4 times maximum aggregate size in the mixture. And considering that the mold in the gyratory compactor is 150 millimeter in diameter. Although all parameters need to be regularly and accurately calibrated, but the gyration angle has the greatest effect on specimen compaction. As the angle increases, the compaction effort increases, and similarly, if the gyration angle decreases, specimen compaction will decrease. Relatively small changes in gyration angle can make significant changes in the compaction level. And ASTO has developed a procedure for evaluating the internal angle of a gyratory compactor. And this should be used to check the gyration angle of compactor, particularly when there are different compactors in the field and in the laboratory. The Superpave gyratory compactor has the ability to accurately measure the specimen height to the nearest 0.1 millimeter after every gyration. And this information is used to estimate the mixture density at low levels of compaction and to document the compaction rate of this mixture. And this is taken on the log scale, that number of gyrations, and this is the percentage of GMM achieved at a particular gyration level. Now this information is important to determine what would be the compaction level at different gyration level. Step 4 is sample preparation and compaction. Several specimens are prepared for design of the mix. 8 specimens to be compacted to end design. 2 specimens for GMM, which are tested but they are not compacted, they are kept loose. 6 specimens for moisture sensitivity testing as per ASTO T283, that is your TSR, and 2 specimens for NMAX verification. For compacted GMB samples, the specimen size is 150 millimeter by 115 millimeter height. So diameter is 150 millimeter and height of the specimen is 115 millimeter for compacted specimen for calculation of bulk density. The mixing and compaction temperature is based on viscosity. Then preparation of mixture. Preheat the aggregate sample in an oven set approximately 15 degrees higher than the mixing temperature. 2 to 4 hours are required for aggregate to reach the mixing temperature. Similarly, preheat the asphalt binder to the predetermined mixing temperature and then prepare the mixture. After mixing of aggregate and binder, the mix is conditioned for 2 hours before compaction, and that is called the short-term aging of the mix. Then place the conditioned mixture at the compaction temperature in the mold in one lift, level the mix and place the top plate in the mold. Load the charged mold into the gyratory compactor, centering it under the loading ram and then compacting. Prepare at least 2 replicate specimens for each trial binder content at the end design gyration level. The specimen which are made for determination of GMB should have height of 115 plus minus 5 millimeter after compaction. And this can be achieved if you place approximately 4,700 grams of mixture into the mold for blends with aggregate specific gravity between 2.55 and 2.7. Set the gyratory compactor to the proper number of gyrations as per traffic conditions, and this I told you earlier also that the number of initial gyrations, design gyrations and maximum gyrations depend upon the design traffic. If it is less than 0.3 MSA, These values are 6, 50 and 75. It is more than 30 MSA. These are 9, 125 and 205. After compaction, remove the mold containing the compacted specimen from the compactor and slowly extrude the sample from the mold. The Superpave gyratory compactor can be set to height mode also instead of number of gyrations mode. And this will cause the molding process to stop after reaching the specified height rather than stopping after a specified number of gyrations. For example, ASTO T283, that is the test for TSR, tensile strength ratio, requires that specimen be prepared at 7% air wires. To accomplish this, the designer must determine the appropriate mass of the asphalt mixture to place in the mold that will result in the proper air wire content at the proper height. Step 5 is Superpave data analysis. Determine %GMM at number of initial gyrations for each binder percentage. And this is the unique step in Superpave mix design. That is calculation of %GMM achieved at different number of gyrations like N initial, N design and N max. Using the data provided by the Superpave gyratory compactor, an estimated mixture bulk specific gravity, let us say GMB estimated, can be calculated based on the diameter of the mold and height of the specimen, that is the volume of the specimen. Now this estimated GMB can be calculated for every gyration, and the final product of the compaction process is an actual specimen with known height at N design. Then you determine the height of the specimen at N design, and let us say this height be H N design. Obtain the height of the specimen at N initial. Let us say this height is H N initial. But one point to note here is that this estimated GMB at initial gyration is assuming that mold is smooth and surface of the specimen is perfect, which is not always true because mold gets worn out with time. And therefore, these surface imperfections are accounted for when the sample compacted to N design is actually weighed in the laboratory. And by using the following correction factor, the estimated GMB at N initial can be more accurately calculated. And the factor is the height of the specimen at N design divided by height of the specimen at N initial. Now using this correction factor, you can calculate GMB estimated at N initial. That is equal to the correction factor multiplied by GMB at N design. And determine the average GMB at N initial for each trial binder content. And finally, you calculate the percentage of GMM value at different number of gyrations using these equations. Percentage of GMM at N initial is GMB at initial divided by GMM at the trial binder content, or it is GMB at N design divided by GMM at trial binder content, or it can be at N maximum also. Remaining volumetric properties like air wires, wires in mineral aggregate, wires filled with bitumen, PBE, filler bitumen ratio, they are estimated in the same manner as in Marshall method of mixed design. For example, effective specific gravity of aggregate is estimated using this equation 100 minus PB upon 100 upon GMM minus PB upon GP. PB is the binder content, GMM is the theoretical specific gravity of the mixture, and GB is the specific gravity of the bitumen. Now GSE is a aggregate property, and similarly you can calculate total air wires in the mix using this equation, that is 100 into 1 minus GMB upon GMM, this is bulk density of the mix, theoretical specific gravity of the mix, and VMA is 100 into GMB into 100 minus PB upon GSB, and this 100 minus PB is nothing but proportion of stone aggregate in the mixture. And BSP here is bulk specific gravity of aggregate. The words filled with bitumen is given by this equation, VMA minus VA upon VMA. VA is the air wires, VMA is the wires in mineral aggregate, and that is wires filled with bitumen. I have uploaded a video on martial method of mixed design, and this is available in Hindi and English both. You can watch that video to understand calculation of all these parameters. Then finally, the results are plotted in the form of air wires versus bitumen content, percent GMM at initial and initial versus binder content, percentage of GMM at end design versus binder content, VFB versus binder content, VMA versus binder content, and bitumen filler ratio versus binder content. And you select the optimum binder content corresponding to 4% air wires at end design, number of gyration corresponding to end design. Then other parameters like VMA, VFB are checked at this optimum binder content, and they should remain within permissible limits. In addition to that, air wires at initial and initial should be more than 11% for design traffic of 3 million or more. Air wires at N maximum should be more than 2%. That means the density achieved should be 98% of GMM. VMA should be above minimum listed, and that depends upon the nominal maximum size of aggregate. VFB should be within permissible limit, and filler bitumen ratio should be 0.6 to 1.2. So that is how you determine the optimum binder content. In addition to that, Nmax parameter must be determined and verified that GMM at Nmax does not exceed 98%. That means the air wires in the mixture at the end of the design life should not be less than 2%. The next step, that is step 7, is moisture sensitivity testing. This moisture sensitivity of the asphalt mixture is determined as per ASTO T283, and this is the method of finding ITS, that is indirect tensile strength, and tensile strength ratio TSR of asphalt mixture, and that should not be less than a minimum specified value in the codal provisions. So friends, thank you very much for watching this video. If you have any doubt, any question, you can write in the comment box.